Okay, so it is the project screen in which you have to drag and drop these components around the screen and you can build your network. And before we are going to proceed, in the upper tab you see there is a ribbon configuration is there. From setting tab, if you go to the setting tab, you will get those icons here. One is unit, ID rules, user, project, configuration, statistics, and other things. So let's say if you have any, you are doing any project or you want any specific unit to assign, so you can always choose the unit here. So here by default there are three types of units are available. In one is standard, one is BTU unit, and is matrix unit. So all units have some different representation of mass, length, and time. So if you want, you can create your own separate unit. Let's say you create a new unit system, you name it and press OK. So that new unit has been created. So you can change the desired unit of the elements what you want to assign, like mass flow rate if you can represent in kg per second or ton per hour, like that. So here you can change those units, and let's say we are changing the pressure unit. In this it is Pascal, and we are changes to bar, and you make it set as active. So whatever pressure component and pressure value will come, then that will be represented in terms of bars. So this unit term is very handy when you are doing a big projects and dealing with a lot of units. So from the last class, I assume we cover up the conduction and convections and those heat transfers, and now we are going to cover the radiations. So here in the right side, you can see this is the master database where all the elements are located. If you go to the flow solvers, there are a lot of components are there in category wise, and among them you go to the heat transfer element. So in this heat transfer element, there are several other sub components are there, like a composite heat transfer, conduction, convection, cross conduction, distributive heat source, film convection, and fluid radiations, and jet impingement convection and surface radiation. In order to model, we use this surface radiation component, and before that we have to create a heat source in which the radiation is going to happen to the heat source to any fluid or any heating medium you want. So in order to model the heat source, you can go to the node and boundary condition, so you just drag and drop one boundary conditions, and if you want you can name it like heat source. Then you can drag and drop a node.
So you move please slowly.
Okay, so from which point I should start again? Okay, so first you can drag and drop a boundary conditions on the screen like this.
How to give that heat source?
Yes, for heat source, you can specify the boundary conditions as temperature like this. So if you click on this properties of this boundary condition, which will come in this left side of the pane, then you can see the boundary conditions options. You can apply the pressure boundary conditions, temperature boundary conditions, mass source, and volumetric flow. So in this case, you can assign the temperature boundary condition. So now it is 273 Kelvin or 0 degrees Celsius. So you can assign it 1250 and change the unit to degree Celsius. So you assign 1250 degrees Celsius in this boundary condition. So this will act as heat source. Okay, so now you can drag and drop a node from this component list. So this configuration along with this boundary condition will be represented as a heat source. Okay, so after that you can again go to this component list and search for the heat transfer. So from this heat transfer, there is one component which is at the bottom of the list, is the surface radiation.
Just a minute. Huh?
Okay. So you can drag and drop this surface radiation onto the screen like this. And
सर
when
एक मिनट रुक जाइए, आप एक मिनट रुकिए. How to change the heat source?
heat source means what thing you want to change, sir? The temperature?
Understood, but how to rename it as a heat source?
Okay, so if you click it, then in left side there will a panel will open.
हाँ.
You got it?
प्रोजेक्ट में जाइए था.
Otherwise you can double click it.
प्रोजेक्ट.
Okay, if you double click it, a windows will be popped out. You got it?
Yes, got it.
Okay, so you can specify this identifier as heat source. So basically it is a naming representation of that component. You can specify the name here. Okay, then you can assign the temperature boundary condition. So it will act as the surface temperature for the radiation. Okay,
Okay.
okay. Then you can go to this component window. So in this component window, in the tree of flow solver, you can go to the heat transfer. So in this heat transfer, there are several heat transfer components are there. Among them, you just drag the surface radiation component. Okay. So you connect to one end in this yellow part, which will be act as the upstream, and drag it to the node. So when you press the mouse and drag it to upon the node, it will create a blue square around the node, and if you leave it, then it will connect. So now we are going to make the fluid flow path. And in order to make the fluid flow path, you can go to this flow solver again. And there is one tree is the costume loss. So you expand that tree and you will see the first component as flow resistance.
Wait, sir. Please explain again.
Uh, which thing, sir? This one, the
Custom
surface,
loss.
this component.
How to go to the custom loss and which components to be taken.
Okay, when you go this component list, you can get this flow solver there. And within this flow solver, you have to expand this flow solver tree. So within this flow solver tree, there is component known as the custom loss here. And
Okay.
if you click the plus sign, the first component will be flow resistance. Okay.
Okay. Flow resistance.
You drag two flow resistance component onto the screen like this.
Okay.
Okay. Now,
Yes. Two flow resistance, correct?
yes, two flow resistance. Now you can see the arrow, for one is upstream and another is downstream. And now you join these two flow resistance component like this. Okay, so the first flow resistance component downstream will be connected with the flow resistance component for the upstream. So in this manner, you can connect it.
Wait. Okay. Go ahead.
Okay, then you go to the flow solver again from this component tree and go to the nodes and boundaries. So at the bottom part, you can get nodes and boundaries. Then you expand the tree. And drag two boundary conditions, one for the downstream and one for the upstream. Okay, then you can
Pratik,
yes,
can you give us can you show other text copy of the problem statement? Likewise, you have done last time when
yes,
you
yes,
have seen the first one-dimensional steady-state heat conduction. Likewise, you are solving now the
yes,
radiation problem. Yeah, yeah.
yes. So radiation problem means that node will be act as a radiation surface. So it will follow this black body rule that E is equal to a um, sigma t to the power 4, and we have to calculate the amount of radiation it has been radiated from that heat source to a stream of flow of water in which the water flow is maintained 10 kg per second. So this is the problem statement and this is our network. So this temperature source is going to radiate heat energy to this
Wait.
Okay.
230.
Okay.
Acha, Pratik,
Yes.
why we are giving two pipes on the right side?
Actually, this
Because
component can only be connected with a node, because this
अच्छा,
component cannot be connected with this flow element. Unlike the previous demo you have
तो
seen,
अच्छा, इन दोनों
the
डिफरेंस में एक नोड के
heat
लिए पूछ
transfer
रहे हैं क्या?
element
That
is
means for node connectivity we are giving it, right?
yes, node
Physically
connectivity.
there is only one pipe, right?
Yes, that is for one pipe.
Yeah, because okay, ठीक है.
Okay. So in this configuration, you put these two boundary conditions. For the one is upstream and another one is for downstream, like this. Okay. So now you can connect this element to the in between node.
Okay.
Okay. So from this statement, we consider the form factor as 1. So whatever the radiation surface is there, so it is totally transferring heat with the full of its surface area. So that's why we make the form factor 1, and the surface area is mentioned at 10 meter square, and we put the emissivity
Wait,
1.
wait, wait.
Or if you want, or if you have any data, then you can put also the emissivity requiring as per the requirement as 0 0.8 or 0 0.9, like that.
Please wait.
Okay.
Go ahead.
Okay, so you can specify the upstream surface area 10 and emissivity 1. Similarly, for downstream you can specify the same surface area and the same emissivity. So in both of cases it is 10 meters square of surface area and emissivity 1. Okay.
Wait. Okay.
Okay, so now let's say we click this flow element. So here the name is coming as flow resistance. So this component is somewhat different from the pipe, that actually it provides a resistance towards the flow, or else you can say it calculate the pressure drop towards the flow, and as per the pressure drop you will get a varying mass flow rate for this resistance which is given by this element. So if you go to this data of this flow resistance component, you can get the resistance data as flow resistance behavior as quadratic, density variation, flow admittance, and admittance scaling factor. So it calculates the pressure drop as the formula of FL by D half rho V square. So it derives from the momentum equation. So from this formula, it calculates the resistance offered, because the frictional losses and head losses is combined as the flow resistance, and this combined effect you can specify here as the flow admittance. So if you put any admittance number here, let's say it is initially 0, means there is full resistance and there will be no flow. And if you increase this flow admittance value, like say 0 to 0.1 to 0.5 or 1, then the resistance is going to reduce and you will get a flow within this element. So this component come in handy in many situations, like you don't know the total dimension of the pipe or any flow medium, but you only consider this flow rate or pressure drop. So in that case you can easily use this component. Since we don't know regarding the dimension of the pipe, like length and diameter of the pipe, but we know the flow is around 10 kg per second. That's why you we use this element. So if you go here, you can specify the resistance behavior as a quadratic, linear, and square root. So from the momentum equation, the pressure drop is directly proportional to the rate of change of momentum. So if you simplify it, it will be directly
Wait,
proportional.
wait, wait. Just show him how that resistance and all those data, how it is visible, from which node and from where we have to click.
So if you click it, then it should come from this left side of pane. Otherwise, you can double click it, then a windows will pop up and you can see the properties of this element. Okay. Okay.
Okay.
So you can make this flow resistance as 0.001, and let's say the volume enclosed by this flow element is zero point 0.1. So you
So resistance behavior is quadratic, correct?
yes, it's quadratic in the terms. If you check the pressure drop equations, which is derived from the momentum equation, so it is a function of your rate of change of momentum. So which will be represent, if you say in the term of formula, it will be FL by D into half rho V square. Okay. So this F represent the frictional losses and rho V is the momentum change. And if you make the density constant, like in case of our water or any liquid, so in that case, that will be the proportional to the
Reynolds number.
mass square M. So you can specify this behavior quadratic, like in term of square, linear, in, in power of 1, there will be no square, and square root. So that power has been reduced to half. So basically, you can only specify the amount of resistance it will provided to the flow path. Okay. So in our case, we specify the flow resistance as 0.001 and the volume of this component as 0.1. Okay. You can put this same data in this upper flow resistance also. So you can double click it. So if you double click it, then another window will be pop up for this upper flow resistance, and you can specify the same data. And the volume will be 0.1. Okay. So now you can assign the fluid. So from the problem statement, 10 kg of water is going to flow within this flow in this flow element. So in order to assign the fluid, you can select any element like this, but that must be including inside the flow path. So you right click it, you can select any component, and you right click it and go to the assign fluid tab. Okay, in this assign fluid tab, if you click it, then a new windows will be pop up like this, and here you will get a flow circuit 1. So in this case, it is our only one flow circuit, so that's why it come like this. The name is flow circuit 1, and under the fluid it is mentioned click here to select the fluid. So if you click, so you can see a drop down list will be there, and this total line will turn into blue. You got it? Hello sir, will you able to follow till it?
Yes, okay.
Okay, so from this drop down list, if you click in this, so you will get three list. In three table you get two phase fluid, pure fluid, mixed fluid, and here it is.
Just show that fluid assigning. Close this.
Okay, you select any component like this, so it will be highlighted like this, and after that you right click it. Upon right clicking, you will get a drop down list, and you go to the assign fluid tab. So you click the assign fluid tab. Okay, so from this assign fluid tab, you will get one flow circuit 1, which is representing this flow circuit. So under this fluid, here it is said click here to select. If you click it, a drop down list will pop up. So like this. So from this drop down list, you select the two phase fluid, and within this category, go to the general, which will be under the master database. And from this, you select the water. So you scroll down a little bit and you will get the water. Okay, so after selecting, this line will be filled like this: H2O, water, general, two phase fluid, and master. You got it?
Wait.
Two phase fluid, general, and water.
Okay.
Okay, so this will come like this: H2O, water, general, two phase fluid, master, like this. Then you click OK. So now the fluid has been assigned to this flow circuit, and what remaining is defining this boundary conditions. Okay, so let's start from this upstream boundary conditions. If you click this first boundary condition, which is at the bottom of this network, or you can double click it, so a windows will be pop up like this. The first one is pressure boundary condition. So in order to maintain the flow, you have to specify two pressures. So there will be a pressure difference created and the flow will happen. So for that reason, we have to assign some pressure at this upstream of this flow network. So go to this pressure boundary conditions, and it is initially not specified. You select it, and after selecting, you will get several values like fixed on user total value, fixed on solver total value, and fixed on user static value. So among them, you choose the fixed on user total value. So this will allow the user to give specify any pressure value in this pressure column. Okay, so you check this unit in this pressure column and select the bar and specify it 1.2 bar. So which is around 120 kilopascal. Okay, after assigning the pressure, we have to assign the temperature of the inlet fluid. So let's say the temperature of water which is going through this network is 20 degrees Celsius, and if you click it in this fixed on user value just like the previous one, then a temperature tab will be pop up at the bottom of this pane. Okay, so in this temperature tab you go to the unit and make it degree Celsius. Okay, and make the temperature is 20 degrees Celsius. So in order to flow this fluid, we get the pressure of 1.2 bar and the temperature of 20 degrees Celsius. Okay, so you check this unit, the pressure unit should be in the bar and the temperature unit in degree Celsius. Okay, so this first boundary condition.
Okay, just a minute. Huh?
Okay,
Suppose I want to give velocity as a inlet boundary condition, then
in this case, sir, you cannot define the velocity inlet boundary condition in this 1D software. So that you can perform in 3D software like ANSYS and
no, but sir, see here. Then how student will study the defect of Reynolds number on heat transfer?
yes, I will cover that in when we are build the Rankine cycle. So we'll use a
That
white
means,
element there.
just a minute. That means this is not possible at all in this software. Variation of velocity, velocity boundary condition cannot be given.
No, no, velocity can be vary, but that velocity is dependent upon our difference in pressure.
No, no, no. It's not. Pressure is different and velocity is different. Pressure and velocity has no relation.
No,
How
I
you
am
can say like that? Flow is taking place. Suppose flow is laminar, then velocity is different. Flow is turbulent, velocity is different.
saying, sir, you
Then
can only assign the pressure boundary condition here.
huh,
So in difference pressure, you will get a sudden amount of flow within this
no,
element. I'm not telling about you can specify the velocity boundary conditions
no,
here.
no. See, listen. What I am saying that velocity may be 2 meter per second at 100 kilopascal. Velocity may be 2 meter per second at 1000 kilopascal.
Yes,
So I'm saying that whether my student will able to study the effect of Reynolds number or not.
yes, you can study the effect of Reynolds number. You can,
How? See, when velocity is not giving, when we are not giving velocity, how Reynolds number will be defined then?
okay, see, your Reynolds number is rho b d by mu. Okay, so from this you have to assign the velocity you have said, but let's say you in this condition you specified two pressure.
Just sir, just a minute. We are discussing. Just a minute.
Okay,
Okay, sir, you continue. Just a minute, just a minute.
Okay. Okay, sir. For your asking, I will show you a small thing. So
Yeah, you just open up different example. We show the velocity related
yes, yes.
example. Yes.
Let me just show you.
You keep this. Keep this. Keep this. We
Yes,
have to cover this
yes, yes.
first.
I keep it. So let's say there is a pipe is there. Okay. So I put a boundary conditions here and another boundary conditions here. Let's say the inlet boundary condition is 1.1 bar and the temperature is 20 degrees Celsius, and the another one is 1.09 bar. So you can specify the length of the pipe. Let's say it is 2 meters and the diameter of the pipe is 0.1 meter. So in our case, in this 1D software, whatever the flow will develop within this pipe, so it will be considered as fully developed flow. So this diameter for the pipe you can consider as the hydraulic diameter of the pipe, and for frictional losses you can specify the roughness of the pipe. So there are several type of
Sir,
losses.
sir,
Yes,
I understood what we are doing.
yes,
You are doing now calculating the pressure drop, and then we are using Darcy-Weisbach equation to find out the value of F. And from that F, you are finding out the velocity, right? What you are doing right now, right?
yes, yes. So
See, I'm saying that there must be some facility to directly input directly given as a velocity as input.
no,
Are you getting my point?
yes, sir, I can get your point, but in the software,
At
it is
least, at least flow rate should be mentioned. If flow rate is mentioned, that's it. Velocity is also known.
yes, you can put the flow rate also here.
No, no. हाँ बताइए कहाँ पे है ये flow rate?
Okay. So let's see. We assign the fluid of water here. Okay. So I
Okay,
assign water in this.
okay.
So if I put the solve steady state,
Hmm.
you get the 18 kg per second of water. Let's say you want to specify the amount of flow rate here.
Hmm.
Let's say 16 kg of water should flow.
हाँ.
So if you make this boundary condition, the downstream boundary condition, here you get pressure boundary condition, temperature, mass source, and volume flow source. So in this mass source boundary condition, you specify fixed on user value. Okay. So here you can see the
Sir,
usage kg per
I
second.
don't know why you are saying no. It is available in the software.
You have asked,
Flow
sir.
rate is given. That's why I'm asking you that velocity is not mentioned, but flow rate is mentioned. Then it's okay.
Yes, I'm that saying. You have, sir, asked how can we directly give the velocity boundary
Ah,
condition.
that's it. So that's okay. That time only if you mention that velocity is not possible, mass flow rate you can given. That's it.
That's thing, sir. I want to show that thing in this small network.
Okay, okay. You continue now over this problem. No problem.
Okay. So here you can specify the mass source let as let's say it is minus 16. So since the flow is coming to this node, so it is considered as negative, and if you put it in this node where the flow is going to flow, then it will be considered as positive. So this upstream node will be positive and this downstream node will be negative for defining the mass source boundary condition. Okay. So if you solve the steady state, you can see you get the total mass flow of 16 kg per second. And if you go to the property and the result window here in this non-dimensional variable pane, you will get this Reynolds number, Prandtl number, and all the numbers from this. Okay. So now coming back to this problem. we'll do this same thing here. We specify the upstream boundary conditions like 1.2 bar and temperature of 20 degrees Celsius. And at this downstream boundary condition, we specify this mass source as minus 10 kg per second. So in similar manner, this flow is going to happen from this node to this node. And since it is the receiving end of this flow, we specify the mass source as negative. So minus 10 kg per second. Okay. So after that, you can solve the steady state. And if you hover your mouse any flow element, you can see the total mass flow is 10 kg per second. And if you click this node and go to the result, you can see the total temperature is raised from
Wait, sir. Go very slowly.
okay. You specify this mass source as minus 10 kg per second for this upstream boundary node. And after that, you click
Wait.
solve steady state. Okay, you got it.
Wait.
In which thing I have to repeat? Please mention. Okay, you specify the mass source as minus 10 kg per second in the upstream element. Hello, sir. Sir, you specified it. So then you solve the steady state.
Okay, wait.
Okay, you did it.
Yes, solved.
Okay. So if you click this node, which is connected between this element and the boundary.
Just a second. Continue.
Okay. So if you click on this node, so you can see from this result pane, which will be at the left side, You able to see it? You just double click it, then a new windows will be pop up, or you can directly go to this left side of the pane. So we'll see the total temperature is 92.6398 degrees Celsius. Okay, so you can apply the MCP delta for sensible heating to check this amount of heat gain throughout this network, or you can just click in this heat transfer element and it will be highlighted like this, and go to the result of this, and you can see the total heat transfer. So if you change this unit to megawatt, then you can see around 3.0416 megawatt heat has been transferred through radiation from this heat source to the fluid element. Okay, are you able to see your result?
Wait.
Hello,
Yes.
Pratik.
Yes, sir.
Now, suppose I want to consider some convection heat losses from this the surface, the black surface. How to
Yes.
incorporate it?
So if you want any convection heat transfer, so there is one element you can see this heat transfer. It's known as the convection. Okay. So if you put this convection like this, and you can specify the convective heat transfer coefficient and the surface area for the convection, then you can also represent the convective heat transfer throughout this network. So this thing can be
Wait. Let me do that. What are the values has to be specified? Please tell
so
that.
you any value you can put. Actually, I don't have any value, so you can specify any random value like say uh, 80 or 50 each convective heat transfer coefficient, and the surface area like say same area you can put the 10 meter square. Okay, so after putting this value, again go to this solve steady state, and again if you check the temperature, it goes from 93 degrees Celsius to almost 104 degrees Celsius. Okay, so in this similar manner, if you click this convective coefficient and goes to this result, and if you check there a amount of heat transfer also there. Okay, Sir, you got it? This convection heat transfer.
Wait.
Okay, sir, you got it.
Wait. Just a second. I will tell you when to start.
Okay.
Result temperature is what? Final result temperature.
Either
Outlet, right? Outlet area. Outlet.
the outlet you can see the previously when the convective heat transfer was not there, so the temperature was 93 degrees Celsius. Now you can get 104.637 degrees Celsius. Okay, so if you click,
Hello, Pratik.
yes sir.
Whatever the value of H, what you have mentioned 50, that is losses from the surface, right?
No, if there will be any fluid medium in between this your radiation surface to this flow network, then this fluid medium you can get this convective heat transfer around
That
50.
means this is heat gain.
Yes, it is heat gain from this heat surface throughout this fluid.
That is
It's
H to be mentioned
water.
negative. ठीक है, okay.
Okay, so this convection will be more prominent if you can actually show any fluid medium. In our case, there is no fluid medium. That's why we choose a small value, and that's why you get around half megawatt, 0.57 megawatt of heat transfer through convection to this network. Okay, okay, sir, you did this network now. Okay, now we are going to proceed to model.
Wait.
Sir, anything you want to ask from this, or should we proceed to the next one?
Pratik sir,
Yes.
now just wait. You just show them which are the tutorials related to heat transfer which we have, step by step guide, so they can perform. Just tell them the example which are there.
Okay. Uh, Actually, that is a mixing of every type of heat transfer element, and the others are there. So in
No,
this,
the PDF files, whatever you have, just show them.
okay. So I think there also they have also the PDF file. So you can go to this Flownex file location. Okay, in this Flownex file location, you get the tutorial folder is there. So in your case, if you install it correctly, then that will be in your local C drive, program files, and within the
No,
Flownex folder.
no problem. No, we had prepared for bits or some institutes and for those exercise.
Yes, so if you request, then we can also send you some tutorials regarding this.
No, right now they don't. They have meeting. So just show them what are the PDF files, what are the example you cover.
Yes, so so
We had prepared that. No, the gesture yesterday shown that.
that one.
Yes, those 4 to 5 PDFs were there. No?
Okay, just wait a minute, sir.
Hello, hello. Am I audible?
Just a second. Sir. Yes,
Yeah.
please go ahead.
So you wanted to see what we can do in Flownex, correct?
Just show them the tutorials which we are having and
Yeah,
the work which is going, the preparation which is going on.
yeah. I just show like this is the kind of a thing we have done, and we have this kind of a presentations or PDFs, maybe 100 around 110 like that available. So like that in this, how we are going to discuss like
This is done.
problem.
This is already shown. Another example.
No, I am just saying. So multiple examples are there. Okay, like this example is there. Okay, like calculate the exit temperature of our ice. You wanted to see what the material we are going to provide like that, or you wanted to check some other, you wanted to solve another problem.
No, no, not problem. Like for example, they said they have like radiation
Hmm.
related example, then convection related example, force
Yeah,
convection related example. So for
yeah.
that's why they were saying transient heat transfer related example. So what we
No.
have already ready or what work in progress going on at our end.
Yeah, yeah,
That
yeah,
clear.
yeah. Yeah. So I just give me a second. Ah. Yeah, so it is just a normal. Okay, it is not extensive. So small problems we have solved. Okay, like water is pumped from a lower reservoir to high reservoir by a pump. Okay, and it is required 20 kilowatt of the useful mechanical power to the water. The free surface of the upper reservoir is on 45-meter higher, and if the flow rate is measured is 0.03 meter
Okay,
cube per second.
okay, got the idea, sir. They got the idea, and
Yeah.
we are just requesting.
Yes, sir. Suraj, your voice is lost.
Wait, sir. I am
Okay, okay,
discussing something.
okay then, no issue.
So, just sir, for
Yes, yes, tell me.
For example, sir, if the institutes are having some 8 to 10 problem statement or
Mm-hmm.
tutorials for heat transfer,
Mm-hmm.
and you can consider 10 plus problems, then
Mm-hmm.
how much time we will require to do a step-by-step guide or tutorial guide for them? How much time?
The like I have shown to you, correct? Um,
10 example, for example,
no,
they
no,
have.
I understood, I understood. Like this kind of a detailed document they want
Yeah,
from
this type of detailed 10 page, 20 page tutorials, correct, sir? According to their experiment
experiment.
number.
Yeah, yeah.
Yes.
I understood. Say the number is 10. Okay,
Yes.
10 different problems are there,
Okay.
and the institute wants the step-by-step procedures, how to model it into the Flownex, and what are the result
Yes.
calculations. They
Yes.
wanted to check that thing, correct? So
Yeah, not research. How much time we at our end will be required to prepare these tutorials for them?
yeah, we are considering ourselves only. Okay.
Yeah.
Yeah, we are considering ourselves only for 10 tutorials. I need to understand what kind of a problem statement are there. Okay. If the
Okay.
problem statements are suppose that whatever we have shown to you, okay, just a
Like that
minute.
only? Will be that
Or
problem?
it's a much detail than that.
Yeah, this level only. This level.
If,
Those will not be that much complicated. Yeah, this level only.
if this is the level, then I guess so within 4 days or 5 days.
4 to 5 days.
Yeah.
8 week pakada sir. Yeah, manual for the whatever the
Everything. Everything.
yeah.
Everything.
So 1 week I can say.
Yeah, 1 week is fine. Means like everything is that. All the step-by-step procedures, how to create, what kind of a things, means like what, from where to drag, what kind of property they have to use, what fluid they have to use. The detailed one, the way it is on the screen. The same one we can provide you in a PDF format. So the student can perform on that.
1 week. Okay. For example, they have like convection, radiation, as well as transient, steady state simulation of simple type which we have shown. So
Yeah,
that type only 1 week will be sufficient, correct?
yeah, 1 week is more
And
sufficient.
I can commit that.
Yeah, you can commit them.
To them.
You can
Okay.
commit
Okay.
them.
Okay. Yes.
Yeah. And Suraj, one more thing I just wanted to add.
Yes,
If
sir.
if suppose that they can give us like the problem statements, okay, like this is the problem statements are there.
Yeah,
So
definitely they will give in advance. No
yeah,
problem.
so what we can do, like I can give a completely what is called timeline, like how much time it is going to take. Okay. So right now
In
seven.
next 2 3 days or Monday, Tuesday, we will get that.
Yeah, if Monday, Tuesday you will give me, so on the same day I can commit the complete days. Okay, like
Okay.
I guess so. If the same problems are there, whatever we have solved here, so it is not going to take much. The larger number you said already 7 days, so not more than that, definitely.
Okay, sir. Thank you.
Okay. So shall we continue this, or we have to stop the our session here?
Yeah. Okay. No problem. Then conclude karo sir session. So we'll conclude the session for today. Okay, sir.
Okay. Okay.
Yeah.
Okay. Not
Thank
an
you
issue.
very much. Thank you.
Thank you.
Ah.
Yeah.